Hello everyone. Welcome to the tutorial. Let's start. Today we will talk about the assignment 5 solution. So let's begin. Okay, question 1. Question 1 is a very simple problem. We want to find out what is the value of phi of 1720. So to compute the Euler function of the number, we just need to factorize the number and then apply the known equation. So 1720, after factorization, we find that it has prime factors 2, 5, and 43. So the phi value of 1720 is simply multiplying 1720 with 1 minus 1 over 2 and 1 minus 1 over 5 and 1 minus 1 over 43. So in that case, we will get the result. So it is equal to 672. So maybe my calculation is wrong, but the idea is something like this. Okay. Okay, so let's see another question. So question 2 actually is a guided question to show that 2 to the power n cannot be equal to 1 modulo n. So to prepare for the result, so we have question 2a, 2b, and 2c. So for question 2a, we assume that there is a value n such that n to the power j will be equal to 1 modulo m, and at the same time, n to the power k will also be equal to 1 modulo the same number m. Based on these two facts, we want to show that n to the power the GCD of jk will also be 1 modulo m. So how can we do so? So it is going to be easy as long as we recall that GCD of two numbers is just a linear combination of the two numbers. So GCD of jk can be expressed as aj plus bk for some integer a and some integer b. So n to the power GCD jk, because GCD jk can be expressed as aj plus bk, so you can write it as equal, so it is actually algebraically equal n to the power j to the power a multiplied with n to the power k to the power b. Now, because n to the power j is equivalent to 1, so it is going to be 1 to the power a, and n to the power k is also equivalent to 1, so it is going to be 1 to the power b, and a and b, they are integers, so in that case, the product of these two will be equal to 1 modulo m, and that is what we want to show. So we want to show that n to the power GCD jk will be equal to 1 modulo m. Okay, so question 2a is done. So let's go to question 2b. Now, question 2b, we want to assume that 2 to the power n is equal to 1 modulo n. In fact, this is impossible. So we hope that by assuming that this is true, we will lead to a contradiction later. Okay, so at this moment, suppose to the contrary that 2 to the power n is equal to 1 modulo n. And if this is the case, then we want to show that 2 to the power GCD of p minus 1n will also be equal to 1 modulo. This time, this is modulo p, be careful, okay? The p here is a smallest prime factor of n. Actually, for question 2b, we don't need p to be the smallest prime factor. We just need p to be any prime factor. But for the sake of getting the contradiction later, let us choose p to be the smallest prime factor of n, okay? So let's see why this is true. So we want to apply the result of Q2A. So Q2A, if we have n to the power j mod m, n to the power k mod m, they are both equal to 1, then we can have something like this mod m. So here, what we want to find out is what happens if we get 2 to the power p minus 1, and then 2 to the power n as well. What happens to these numbers when they are modulo p? So first of all, 2 to the power p minus 1 will be equal to 1 modulo p. This is Fermat-Little theorem. Now, we also have 2 to the power n, which is equal to 1 modulo n. This is from the given fact. So n divides 2 to the power n minus 1. But because p is the prime factor of n, so when n divides 2 to the power n minus 1, then p will also divide 2 to the power n minus 1. So that means that we have 2 to the power n will be equal to 1 modulo p. Now we have the first line, we have the third line, so we can now apply question 2a directly, so that we get 2 to the power GCD of p minus 1n will be equal to 1 modulo p. Okay, now we are nearly ready to arrive at the contradiction. Okay, so recall that p is the smallest prime factor of n. So that means what? That means that p minus 1 will be smaller than p, right? So that means that p minus 1 cannot divide n. If p minus 1 can divide n or has common factors with n, then that means that n will have an even smaller prime factor. So what does that mean? So it means that GCD of p minus 1n will be equal to 1 by our choice of p here. But notice that 2 is equal to 1 is impossible, because if this is true, then what does that mean? It means that p can divide properly 2 minus 1. P can divide properly 1. It is impossible because p is a number strictly greater than 1. So in that case, we arrive at the contradiction of here. Okay, here. This is the contradiction. Because the contradiction is based on this assumption, so this assumption is wrong. So it means that 2 to the power n cannot be equal to 1 modulo n. So this is question 2. Now question 3 introduces a concept called perfect number. So what is a perfect number? A perfect number is an integer, a positive integer, such that the sum of all proper divisors of this number is equal to itself. So we have two examples here. 6 is a perfect number because the proper divisors of 6 is 1, 2, 3. So there are nothing more, nothing less. Okay, 1 plus 2 plus 3. It turns out that it is exactly equal to 6. Another example is 28, because 28 can be expressed as the sum of all its proper divisors. Okay, so we are going to look at a result that was proved by Euler a long time ago. Euler finds out the exact characterization of an even perfect number. Okay, so here we focus on even perfect number. So suppose that n is a number such that n can be written as 2 to the power m multiplied with 2 to the power m plus 1 minus 1. We want to show that if the latter part here is a prime number, then n will be a perfect number. So as long as this is a prime number, then n of this form will be a perfect number. So how can we show? So we can show this by brute force approach. We just try, okay, so recall that here we assume that 2 to the power n plus 1 minus 1 is a prime. So we let p to denote this value, which is a prime. Now when p is a prime, then the proper divisors of the original number n will be, so if we look at this, n will be of this form, 2 to the power m multiplied with a prime p. So we know that what can be the divisors? 1, 2, 4, 8, 16, and so on and so forth, up to 2 to the power m. And also, all these numbers multiplied with p. So these are the divisors of n. So the divisors will be 1, 2, 4 up to 2 to the power m, p, 2p, 4p up to 2 to the power m times p. But if we want to count proper divisors only, we omit the last one, 2 to the power m times p. So the last value here that we should consider is 2 to the power m minus 1 times p. Is that okay? So we don't have 2 to the power mp. So the largest one here is 2 to the power n minus 1 times p. So if we sum up everything on the top row, then we get 2 to the power n plus 1 minus 1. If we sum up everything in the bottom row, then we will get, how many p's are there? There will be 2 to the power m minus 1 p's. And this value is p, right? So this is 2 to the power m minus 1p. So if we add them both, then we will get 2 to the power m times p, right? And 2 to the power m times p is exactly n. So by brute force counting, brute force approach, then we can find out that question 3a's claim is correct. Okay? Okay, so let's go to question 3b up to e. So question 3b up to e, we'll talk about the other way around. So A part tells us that if n obeys this property, 2 to the power n multiplied with a prime, and this prime turns out that it is equal to 2 to the power n plus 1 minus 1, then it is a perfect number. Now question 3b up to e proves the other way around. It shows that if n is a perfect number, and then n is written in this form, it gives us a characterization of what happens when n is an even perfect number. So we go to the other way around. Okay, so let's go to question 3b. Okay, so suppose that n is an even perfect number, and then n is written as 2 to the power m multiplied with some odd integer q. So we want to find out what can this q be. So we want to show that this q must obey the form that it has to be 2 to the power n plus 1 minus 1, and such a number has to be a prime. So this is the purpose of question 3b up to e. So at this moment, we assume n is just an even perfect number, and n, if we take out all the 2's, then the remaining odd integer left is q. We have a notation, sigma of q, to be the sum of all divisors of q. So sigma has a sound as sound, so it represents a sum. So it is sum of divisors. Okay. So we want to show that 2 to the power n plus 1 q is equal to 2n is equal to 2 to the power n plus 1 minus 1 times sigma of q. So why is it true? Now the first equality is simple because n is equal to this one. So 2n, you multiply 2 here, you multiply 2 here, so you get this one. So why is the latter true? Okay. So the latter is true, it is because let us find out what can be a divisor of n. So what can be a divisor of n? So the set of divisors of n, so a divisor of n must be of the form 2 to the power something, this j is a number, an integer between 0 up to m, any integer between 0 up to m, and then multiply with some q, where q divides q properly. So in such a case, we can compute all the divisors of n, and then we sum them all up. Then this should be equal to 2n. It is because n is a perfect number. So if we sum all the divisors of n, including itself, it will be 2n. And then if we want to sum all the divisors of n together, then we sum all these numbers up. So we will have 2 to the power j for any particular j, 2 to the power j multiplied with a divisor of big Q. So we will have a term 2 to the power j times sigma of Q produced from this set of divisors. So if we combine all the divisors together, it will have these many copies of sigma Q. So you can show this easily that it is true, okay? Okay, now question 3c is, the conclusion here is the red part. So let's see what it means. Okay, so from part B, we know that this is true. 2 to the power n plus 1 q is equal to 2 to the power n plus 1 minus 1 times sigma of q. Now we know that this number is odd. So this number divides properly the whole thing, but this number is odd and this is just 2. So the GCD of this one and this one is equal to 1. So what does that mean? It means that this number, 2 to the power n plus 1 minus 1, this number divides big Q properly. Okay, so this is what we can get. The conclusion of question 3c is this one. By noticing that, so the key point that we notice here is big Q can be expressed as 2 to the power n plus 1 minus 1 multiplied with some number. Okay, so here, so now we assume that big Q is equal to 2 to the power n plus 1 minus Q multiplied with some number little q. Then we claim that we have the following result. This one is equal to this one is greater than or equal to this one is equal to this one. Okay. Now, so I have listed out the reason for each part. Okay. So this red part is easy. Little q plus big Q. So you add little q here. Little q plus big Q is you add q here. So after that, you get this one. So it is just simple algebra. This is greater than or equal to, we claim that sigma of big Q is greater than or equal to little q plus big Q. The reason is that little q and big Q both divide this big Q. So the divisors of big Q include little q and include big Q. So if you want to sum up all the divisors, it has to be at least little q plus big Q. Okay. So the blue part then we simply substitute this big Q is equal to this one into the result of question 3b. So question 3b, this one. So we replace this big Q as 2 to the power n plus 1 minus 1 close bracket multiplied with Q. So after cancellation of this term, then we will get this result. So all of them are easy. Okay. Now the key point here is for D part, we have established that this is true as always, but then we find that the leftmost term is equal to the rightmost term. So what does that mean? For them to be equal, it forces the middle part, this is greater than or equal to sign, it has to be equal. It has to be equal. So what does that mean? So it means that sigma q has to be equal to little q plus big Q, and then this sigma q cannot have more than 2 factors. It will have exactly 2 factors. One is small, one is large. Is that okay? Otherwise, you will have something more to add. If big Q has exactly 2 factors, what does that mean? So it means that Q is a prime. And moreover, this Q is a prime. Q is a prime. This little q is equal to 1. So Q must be of the form 2 to the power n plus 1 minus 1. So we are done with the derivation of everything. Okay? Okay, now question 4 is an exercise of the RSA crypto system. So here we are given that the public key is EN with E is equal to 211 and then N is equal to 2419. So to see how this RSA crypto system works, so we first find out the factorization of N. N is a product of 2 primes, so it is equal to 41 times 59 here. Based on N, we now know N. We know how to factorize N. We can easily compute phi of N. Phi of N is simply this 1 minus 1 multiplied with this 1 minus 1. So it is equal to 2320. Now with E here and with phi of N here, we can compute D. D is a number such that D times E is equal to 1 modulo phi N. Remember, to compute D, we need modulo phi N. Okay, so we can use the Euclidean algorithm, the extended Euclidean algorithm, to find the value of 11 here. Or, if you are very sensitive, you will quickly see that 211 multiplied with 11 is 2321. So it is exactly giving us the solution. So by eyeball, you can quickly get 11 here as well. Okay. Now once we are getting the value of N, phi N, and D, then we are ready to do the decryption. So here, these are the ciphertexts that we obtained in the problem. So if we want to do the decryption, we raise C to the power of D and modulo N. So these are the values that we obtain. Okay, so how can we obtain this one? You can use your calculator, or even faster, you can write a very simple program to do so. 11 is small, so you don't need to have the fast exponentiation algorithm. You just blindly compute C multiply itself every time you take modulo 2419 and find out the result. The question here is, what is the message that we are encrypting? So if you are sensitive here, all the numbers here seem to be representing the ASCII code of a character. So if you go back to ASCII, you get this is the correspondence of the character. So this is the answer for question 4. Okay, finally, we have question 5. Question 5 talks about an interesting way to shuffle a deck of cards. So we assume that we have 2n cards to begin with, and after the shuffling, we transform the original permutation of 1, 2, 3 up to 2n into, we get the even numbered cards first, 2, 4 up to 2n, and then the odd number of cards afterwards. So basically what we are doing here is we are separating or dividing the deck of 2n cards into two parts. One is having 1, 2, 3 up to n, and then the other is having n plus 1 blah 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 up to, did I make a mistake here? Yeah, that's true. So let me see. So my labeling is wrong here. So forget about it. So the perfect shuffle should not get this. Sorry. So let me quickly type what should the perfect shuffle to get. So a perfect shuffle should get what? It should get. So you begin with 1, 2, 3. So you get. Let me see. You should get n plus 1, and then 1, and then n plus 2, and then 2, and then n, and then n plus 3, and so on. Let me see. Sorry for the mistake here. And then in the end, what do we get? In the last card, we will get 2n, and then n. So this is what we should get. Okay, sorry for the mistake. So I think this is what we. So yeah, it looks like so. So let me get a 3 here as well. Okay. Yeah, I'm really sorry about the mistake. So it should be this one. So let me quickly correct it. Okay, so it is this one. Okay, so the deck of cards are divided into two parts with 1 to n on one side and n plus 1 to 2n on the other side. And after that, we mix the card perfectly so that n plus 1 will become the top card after it is 1, and then n plus 2, and after that it is 2, and then after that it is n plus 3, and then 3, and so on and so forth. And up to the end, you will see that you will get 2n as the second last card and n as the last card. Is that okay? So this is the so-called perfect shuffle method. And then we want to show that by performing perfect shuffle enough number of times, we can get back to the initial ordering. So we start with this one, perform perfect shuffle to this one, perform perfect shuffle again and again and again. And after some number of steps, we will get back 1, 2, 3, 4, 5 up to 2n. Okay, why? Okay, so to do so, we can visualize this as a graph problem. We can construct a directed graph G such that each vertex represents a permutation, and then each edge pointing from U to V, it means that the permutation U will change to V by using one perfect shuffle. Is that okay? So we will think of this one. There will be a vertex corresponding to this permutation and the vertex corresponding to this permutation, and then we draw an arrow from this to this one. Is that okay? Okay, now we will see that for each vertex V, the in degree of V and the out degree of V will always be equal to 1. The reason is that if you have a certain permutation, we know exactly what it will become after one perfect shuffle. And actually, from a certain permutation, we can deduce what kind of permutation, so that after one perfect shuffle, we will get into the current one. So it must be one permutation corresponds to one other permutation. So in that case, each vertex will always have in degree and out degree equal to 1. Now for a directed graph with this behavior, then this graph must be formed by disjoint cycles. And what does that mean? Disjoint cycles, it means that if we start from an initial ordering, after moving some number of steps, it will go back to itself. So done. So this is what we want. But then if you know how to solve question 5b, you can prove 5b directly. So you can use the result of 5b to represent that 5a is also true. So let's see. So 5b says, suppose that x is the minimum number of times to resume the initial ordering. And then we want to find out what is the relationship between x and n. Okay, now there is a key observation. We see that k will move to position 2k after one perfect shuffle. So what does that mean? Okay, so 1 is at position 1, but after one perfect shuffle, it goes to position 2. 2 is at position 2, but after one perfect shuffle, it goes to position 4, and so on and so forth. Now, this is true for all the numbers from 1 to n. But how about n plus 1? N plus 1 goes to 1. And actually, for n plus 1, it is also true. It is 2 times the value of k, but then we want to take modulo of n plus 1. So if we start with n plus 1, then 2 times n plus 1 is 2n plus 2. And then after taking modulo of n plus let me see, n plus 1, you get to let me see, so it's modulo, let me see, sorry, it's not modulo n plus 1, I'm sorry, it's modulo 2n plus 1, yeah, I'm sorry about this. Okay, so 2 times n plus 1 is 2n plus 2, so after modulo of 2n plus 1, then you get into position 1. Okay, so in that sense, x will be the minimum j such that 2 to the power j will be equal to 1 modulo 2n plus 1. Is that okay? Because you want to find out, okay, so k will move to 2k after one perfect shuffle. It will move to 4k after 2 perfect shuffles, 8k after 3 perfect shuffles, and so on and so forth. We want to find out what is the j, the minimum j, such that 2 to the power j is equal to 1. So if we can find out this j, this will be the minimum number of times that we need to do such that every card, every value will go back to its original position. Yeah, I think, yeah, that's all for today. Sorry for the many mistakes. I'll make corrections to the slides and then get back to you. Oh, okay. Okay, thanks all. So that's all for today. And then we will release the last assignment today. So next week, we will have our lecture summary on Thursday, and then slight change about the schedule. So for next week, next Tuesday will be Happy New Year, thanks. So next Tuesday, it will be something for fun. And next Thursday, we will release the homework 6 solution. Okay, thanks all. Happy New Year to all. Okay, see you on Thursday. Yeah.